So finally, we are going to move on to having a look at power. So power is the probability that we reject H0 when in fact it is false. So that means that we are concluding that we have found an increase or a decrease or a change, and that is in fact correct. And this is quite an important thing, especially if your hypothesis test is being used in a scientific way, because the stronger the power, the more likely you are to be correct. And in a medical setting, that's very important. If you're saying that your drug works better than a drug that is already on the market, then you need to make sure that your power is high enough so that your test was most likely correct, because otherwise people are not going to benefit from the side effects from using the new drug over the old drug. So if we have a hypothesis test is classed as good if the power is over 0.8. This is in a medical setting. It should be more than 0.8. We'll talk about this a little bit further down. Usually power is between 0.4 and 0.6. And this is okay. If your hypothesis test isn't being used in a medical setting, then a power of between 0.4 and 0.6 is okay. So if the hypothesis test is less than 0.4, then we usually conclude that the hypothesis test was not good. And as I said before, in science, we need the power to be greater than 0.8 so that we've correctly rejected and our result is valid. So it's quite important that when you find out the power of your hypothesis test, that there are some things that you can do to help you increase that. So we have a set of ways that we can increase power. So if we increase the sample size, this is often an easy way to increase the power, as it decreases the spread of the means. And if you think about central limit theorem, that makes sense, because our standard deviation for the spread of the means of the samples is our original standard deviation of the population divided by the square root of the sample size. So the bigger that sample size is, the bigger the number that you are dividing your standard deviation by, and therefore the more compact your means end up being. Another way to do this is to increase the significance level, which remember is your alpha. This will also increase your power, as when we increase the significance level, we decrease our chance of making a type 2 error. So by this, I am meaning by using, let's say, 10% instead of 5. So you are increasing the chance of making a type 1 error whilst decreasing the chance of making a type 2 error. This has the issue, however, of making a chance of making a type 1 error more likely, like I just said. We could also improve the process used. So this could mean decreasing the standard deviation where possible. We could also choose to have a large value difference between the population means. So if we are using a normal hypothesis test, if we have a large value, or a large difference, between the value that we are testing and the actual value, then that's going to increase the power. But again, sometimes this can mean that our hypothesis test would not make much sense. If I think that the mean is less than 50 on a hypothesis test, so that would be my H1, and the actual mean ended up being 20, there's a big gap there between the true mean and the mean that I've used in my hypothesis. But have I actually been testing something that was a sensible thing to be testing anyway? So you have to make sure that your test is still making sense. And a good way to do this as well is to use a directional hypothesis test. We talked about this briefly when we were looking at the probability of making a type 2 error. So if we use a one-tail test instead of a two-tail test, this is going to decrease, it's going to increase our power, but again, this cannot detect the different in the opposite direction. So if we have a two-tail test and then we say I'm going to change it from a two-tail test and I'm just going to have a look for an increase, and in fact in reality there was a decrease, then you're completely going to miss that side of the hypothesis test. So you do need to be careful that if you're changing a hypothesis test from a two-tail to a one-tail, that you are choosing the correct direction to have your one-tail in. So power is found by doing 1 minus beta, which means that we are doing 1 minus the probability of making a type 2 error. So you'll notice in this section we haven't got loads of questions because we spent so long having a look at the different ways that we can calculate making a type 2 error, and the fact that power is just 1 minus this probability. I'm hoping that as long as you get used to this and get used to what numbers we end up with and how we interpret them, that should be enough. So our first example is that we have a takeaway receives an average of 4 orders every 30 minutes. It is thought that a new competitor has opened, which is going to decrease the number of orders received. If 2 or less orders are received in a 30-minute window, then the average is thought to have been reduced. The actual mean number of orders per 30 minutes is now 3. What is the power of the hypothesis test? So if we were running a hypothesis test on this, it's a Poisson distribution because we just have a constant average rate. We are starting off with x follows a Poisson distribution with a parameter of 4. Our H0 would have been that lambda equals 4. Because we think it's decreased, our H1 is going to be lambda is less than 4. We are then told if 2 or less orders are received in the 30-minute window, then the average number of orders is thought to have reduced. So that is our reject H0 section. So reject H0 is that x is 2 or less, so less than or equal to 2. From this, we can say that the accept H0 region is that x is going to be greater than or equal to 3. We can replace our H1 because we know that the true mean is 3. So now we are using x follows the Poisson distribution with a parameter of 3, and we're trying to find the probability that x is greater than or equal to 3. So we're going into dist, across to Poisson, PCD. Our lower is 3. Remember that Poisson doesn't have an upper limit, so we're going to have 9999999 for our upper limit. And our lambda is 3. Remember, if you have the old version of the calculator, you are going to have to change this to be 1 minus the probability of x being less than or equal to 2. 2 will go in for your x and 3 will go in for your mu. So once you have that, we know that beta, our probability of making a type 2 error, is 0.5768091. And as always, because we are doing a further calculation for this, I have wrote down everything that came up in my calculator. So now power is 1 minus our 0.5768091, which to 3 significant figures gives us 0.423. If we were then to interpret this, if we were being asked if our power was good, if what that told us about our hypothesis test, so in this case, our hypothesis test is okay as the power is between 0.4 and 0.6. And this isn't a medical test that we've been looking at, it's just a general hypothesis test, so it didn't have to be any larger than that. Having a look at the second example, we've got the mean age of a person learning to ski is thought to be less than 20, with a standard deviation of 5 years. A test is performed at a 5% significance level using a sample of 4. So we're starting off with x follows the normal distribution with a mean of 20 and a standard deviation of 5 divided by the square root of 4. And remember that it's actually a variance that you write in your distribution. So if we were doing a hypothesis test here, our H0 would be that mu is 20. We're seeing if it's less than 20, so our H1 would have been that mu was less than 20. So if we had our normal distribution with our mean in the middle, we're wanting a value that makes it, because it's a 5% significance level, so that we have 5% down here. So we're going to go back into dist, norm, inverse normal, because I know the area, I'm trying to find this value here. So here my tail is going to the left, my area is 5%, so 0.05. My standard deviation is 5 divided by the square root of 4, and my mean is 20, which means that this value here is 15.887869. I'm wanting the accept H0 region. So remember that bit that I've coloured in red there is my reject H0 region. So I'm wanting x to be greater than 15.887869. We're then told that the actual mean ended up being 18. So our H0 should have been, our H1 should have been that mu was actually 18. So then we are using the distribution that x follows the normal distribution with a mean of 18 and the standard deviation is still the same. And we're trying to find the probability that we're in our accept H0 region. So we're going back into NCD. Our lower is 15.887869. Our upper is going to be a really big positive number. Our standard deviation is going to be 5 divided by the square root of 4 still, but our mean is now 18, which means that beta is 0.8009371. We're asked to find the power, so the power of this hypothesis test is going to be 1 minus 0.8009371, which ends up giving us 0.199. So in this case, our power is really small, so the test is not very valid. As the power is below 0.4. So now I'd like you to pause the video and give the 2 Now You Try questions a go. So hopefully you've paused the video and you've given the 2 Now You Try questions a go. So for our first Now You Try, we have a teacher believes that the average of 2 pupils per lesson request to go to the toilet. Towards the end of the academic year, the teacher believes that the number has increased. A teacher decides that if 4 or more pupils decide to go to the toilet in a lesson, then the average has increased. So to start off with, our H0, if we were doing a hypothesis test with this, would have been that lambda equals 2. Our H1 would have been that lambda was more than 2. So 4 or more is our reject H0 region, which means that less than or equal to 3 is our accept H0 region. It is then decided that the actual average is 3. So that means our H1 should actually be that lambda equals 3. So then in Poisson, we should be having 0 as our lower, 3 as our upper, and our lambda as 3, and that gives us beta, which is 0.6472318. To find the power, we have to do 1 minus that value, which gives us 0.353 to 3 significant figures, which means that the test is not very valid as the power is below 0.4. For the second Now You Try question, it is thought that 35% of 12-year-olds had read the Harry Potter book. Due to the films being released, it is believed that the value has decreased as some will now watch these instead. A random sample of 20 12-year-olds is taken, and if less than four have read the book, then it is believed that this is true. So our H0 would have been that P is 0.35. Our H1 would have been that P was less than 0.35. We're told that our reject H0 criteria was that X was strictly less than 4, which means that our accept H0 criteria was that X was greater than or equal to 4. We are then told that the actual probability is 30%, so our H1 should have been that P equals 0.3. So we're then using the distribution of X follows the binomial distribution with an N of 20 and a probability of 0.3, which then finding the probability of X being greater than or equal to 4 gives us a probability of making a type 2 error of 0.89291319. To then find the power, we're doing 1 minus this probability, which leaves us with 0.107. And this time the test just isn't valid. That power is very small. So the hypothesis test is not very good at all. Now, please bear in mind that you can be asked to find the power of a lot of different hypothesis tests. You could also just be given the power and asked to interpret it, in which case you need to read the circumstances very carefully to be able to tell is it a medical setting, in which case it needs to be above 0.8 really. If it's not a medical setting, then is it between 0.4 and 0.6, as this is the usual range. If it's above 0.6 and not a medical setting, then that is a very good hypothesis test. If it's below 0.4, regardless of the setting, it is going to be not a valid test. So please make sure that you are very comfortable with how to find the probability of making a type 2 error, because that is how we can then find our power. Thank you very much for listening.